Hi there, this is part 4 of the development of a power monitor for DC. This episode focuses on accuracy and calibration procedures only. Last time I said I would add more usage demos and examples and so on, but on second thought it might be better to wait a bit until I have had the chance to use it myself for longer. In any case, I think the current menu system is pretty straightforward, and if you decide to build it using the information on part 3 and this video, you will have a very capable little unit in your hand. So let's get right into it. Let's start with a quick look at the input section from the last video. On the right here you see the relevant diagram from the INA 219 datasheet and a quote from the paragraph discussing filtering. Well, it turns out that normally these resistors should not have a significant effect on accuracy, except in the case of the INA 219 they unfortunately do. To understand why, here's a quick look at the INA 219 electrical characteristics from the datasheet. The key are these two fields describing the input bias current on the IN plus and the IN minus pins. You notice that they are not identical, as you might expect. They both draw 20 microamps, but the IN minus has an additional 320k resistor in parallel. This is what this looks like when hooked up to my input filter. If you assume a V-bus voltage of say 12 volts and no load, then you can easily calculate the VIN plus and VIN minus voltages. VIN plus is straightforward. Using the 20 microamps constant current offset, we can calculate the voltage drop over the first 10 ohm resistor, which is a constant 200 microvolts. So VIN plus will always be 200 microvolts less than V bus, and in this case 11.9998 volts. VIN minus is more complicated. To get it, we need to calculate the voltage drop across the combined shunt and second filter resistor and subtract it from V bus. That current in turn is made of two components, the constant 200 microamps as for VIN plus and the current flowing through the three resistors, the shunt, the second filter and the internal 320k resistor in series from V bus to ground. If you do the calculation, you end up with this number here for VIN minus, and if you subtract VIN plus from VIN minus, you get a difference of 380.74 microvolts. Now here's an important thing to understand. This is not the real difference between the shunt, but rather the one that the chip sees at its input. And since we have told it that there's a 0.1 ohm resistor across it, it proceeds to calculate an offset current by dividing 380.74 microvolts by 0.1 ohm to get 3.81 milliamps, even though there is actually no load connected. That offset current depends on V bus, because as you have seen, while the drop over the first filter resistor for VIN plus is constant, the drop over the second depends on the term that has V bus in it. So we can expect to see an offset of 0.65 milliamps to 6.33 milliamps for V bus ranges from 2 to 20 volts. In this test, a variable voltage supply is connected to the red and black terminals. No load is connected. Changing the bus voltage produced the expected offset current. To be true, this is how I discovered the problem, and only later, when I searched about it in some forums, somebody else pointed out the theory behind it. Texas Instruments now recommends not to use a filter with the INA 219 unless you really have to. If you remove the two 10 ohm filter resistors and replace them with wire links, the situation is better, but by no means perfect. The offset current is now in the 50 microamp range and still depends on V-bus, and we have lost the filter. Are there any other alternatives? Well, obviously the problem is caused by the imbalance of the 320K resistor on Vin-, which, by the way, is the resistor that is used to measure V-bus. So in fact the real problem is that the same pin is used for two purposes, and other models of the INA series have apparently moved the V-bus measurement to its own pin. Well, there's nothing we can do about the unbalance caused by the built-in 320K on Vin-, but what if we restore symmetry by adding an external 320K resistor on the other input? I have rigged the unit to allow an external resistor directly between the INA219 Vin plus input and ground. I did not have a 320K resistor, but let's try 330K first. The offset drops from about 3.9 milliamps to 300 microamps. Now a 300K resistor instead, and the offset is now just minus 100 microamps. To examine this better, I've created this spreadsheet. On the top you see the input parameters, then we have a table for V-bus ranges from 2 to 20 volts in column A, column B and C to E contain the familiar formula for the offset calculation with the filter resistors. The 12 volt V-bus is highlighted in yellow. Ignore the rest for the moment. You see the calculation of the familiar offset values in this case. If I change the filter resistors to 0, meaning no filter, column E now contains the other familiar set of offset values in the microamp range. Let's put the filters back in and look at column G2I. This is the calculation using an external resistor Rx on Vin plus with 12 volts and 330K, which should see 171 microamps. We saw plus 300, and there's a reason for this difference, but for now let's just say it's certainly in the right ballpark. For 300K Rx, the expected value is minus 192 microamps, and we saw minus 100, so again it's about right. What about 320K? Hey. Now the values are exactly the same as for the no filter case, except we still have our filter. Now comes the real trick. What if we make the Vin plus totally symmetric to the Vin minus by changing our filter 1 from 10 to 10.1 ohm? In other words, add the value of the shunt. Hey, look at that. No more offset across all V-bus ranges. A perfect solution, but maybe not very practical, especially if you want to change shunt resistors. Instead of slightly increasing the filter resistor, we could try a slightly increase of the offset current through it to get a similar effect. I experimented with that and it works, but there is no point considering it because it again is something that would need readjusting for different shunt resistors as well, and only getting diminishing returns. This brings me to the last part of this spreadsheet, the resolution of the current measurement. There is no much point to finding ways to reduce the offset below 100 microamps. With 10 microvolts, least significant bit, the LSB for current at a shunt for 0.1 ohm is plus minus 100 microamps. This explains the deviation between the calculated offset values in the microamp range and the actually observed values. Just to prove that you actually can do an easy exact compensation for a given shunt and bus voltage by using a series circuit of a 300k resistor and a VR of 20k. Simply adjust the VR until the displayed offset becomes 0. So what is one to do then? The situation with the 0.1 ohm shunt has already an unacceptable high offset current, and with a lower shunt of 5 milliohms, this is going to be much worse. Option 1 is to remove the filter once and for all, which reduces the offset current below the least significant digit. Option 2 keeps the filter but adds an external 320k resistor to VIN+. That should theoretically work and give the same error as option 1, with the benefit of still having the filter, but the effect depends on having exactly the same resistor value on both inputs, when one is an external discrete resistor and the other one buried inside a chip. I found in my model that a plus minus 1% deviation from the 320k already increases the error noticeable for low shunt resistors, and we don't even know the exact value tolerances and temperature drifts of the in-chip resistor. In the end, I decided that the safest bet is to remove the filter, and this is the modified input schematics from part 3. I decided to keep the clamping diodes for now until I get around designing a better input protection. The two 10 ohm and 100 NF capacitor that made up the filter and the wire harness from the input terminals to the PCB where the filter was, and then to the INA 219. The reason why the latter had to go was because despite twisting the wires, the INA 219 picked up a lot of noise over such long wires. The PCB completely stripped off the filter. Originally I had just replaced the resistors with bridge wires and left the input protection in place, but since we are measuring really very tiny voltages with 10 microvolt resolution here, any noise or stray voltages are picked up as well, and the longer the wires. So the necessary reduction of the wiring length meant the diodes had to move as well. Here they are, directly at the terminals, and the wiring to the INA 219 is now a very short and shielded piece of twin-ax cable. The twin-ax goes directly to the INA 219, so that the only longer wires left are just two ground wires, going from the inputs, one from the black terminal, which goes via the fuse to the ground, and the second one is the ground for the diodes and the cable shield. Success! When shortening the input, the display is now absolutely stable. Previously, the picked up noise would cause the numbers to jitter very noticeably, even with a shorted input. Before diving deep into the calibration, let's sort out some seemingly conflicting data. A 12-bit ADC would not have an LSB of 4 millivolts for the bus voltage, but 7.8 millivolts, which is almost double that. The same is the case for shunt voltage. Since shunt voltage is signed, the remaining 10 bits can get you only an LSB step size of 19.5 microvolts, not 10 microvolts. The important clue is this statement in section 8.4.1, which explains that the INA 219 uses actually a delta sigma converter, which could be described as a 1-bit ADC, but with all kinds of clever signal processing and lots of oversampling, you can get pretty much any resolution you want if you give it more time. This also explains this table showing that the resolution is programmable and higher resolutions just take more time. The exploring of delta sigma ADCs and how this works in the INA 219 is a fascinating topic all on its own, but I'm not going to do it in this video. I'm just showing briefly the difference it makes to the accuracy expectation with respect to the different current measurements ranges in the INA 219. If you take a conventional ADC with a programmable gain amplifier or PGA in front to measure, say, a slowly increasing voltage in the 40 millivolt range, you get a string of numbers at the output that corresponds to the blue line of the diagram on the left. To select the 320 millivolt range, you instruct the PGA to divide the input signal by the factor of 8. If you measure the same slowly increasing voltage, you would now get an output that looks like the red line. It would have a very noticeable jump. Also, each point on the red line would have 8 times the value of the blue line. In other words, the LSB is 8 times more. This is not what happens on the INA 219. This diagram is an actual measurement I did. The y-axis shows the value of the shunt voltage resistor, and the measured current goes from about 2 milliamps to 25 milliamps, so very small currents. The blue line uses the PGA in the 40 millivolt setting, that is a current range of 0 to plus minus 400 milliamps, and the red line uses the PGA in the divide by 8 setting, or plus minus 320 millivolts, equivalent to a current range of 0 to plus minus 3.2 amps. As you can see, the lines are almost on top of each other. No jumps or any other deviation, even though we are actually measuring 2 milliamps in the 3.2 amp setting, which is quite an amazing feat. There is a price to pay, and in this case it's mainly conversion speed. The INA ADC isn't very fast. With good resolution we are talking about 2000 measurements per second or so maximum, but even that rate may need to be reduced further if we are trying to reduce noise. To demonstrate this, I just put a constant 50 milliamp current from a power supply through the INA 219 terminals and sampled the data from the shunt voltage register at 10 times per second for about half a minute. The plots show the difference from one sample to the overall average in LSB or 10 microvolt steps. The blue set was recorded with the ADC averaging and sampling setting to 1. The red data used an averaging with 16 samples, and the blue used the averaging with 64 samples. You can immediately see from these plots that the noise goes down the more samples are used for averaging. The distribution of bit differences is also interesting. Ideally, you would like to have all samples having a bit difference of 0, that is, all show just the same true value, or in this case 50 milliamps. In this diagram, the x-axis represents the distance in LSBs from 0, and the y-axis is the number of times showed that this difference showed up, positive or negative, summed together. The blue or noisiest case is generally more spread to the right towards higher LSBs and more likely to be at 1 or 2 LSBs off the value than actually be at the value. The red case with less noise is more often at around just plus minus 1 LSB of the true value. The green case with the least noise peaks prominently at 0, which means the actual value. Sadly, all this noise reduction comes again at the price of increased conversion time, so just setting it once may not always be right for everything. For this reason, I changed the software to allow the number of samples to be changed in the setup menu. Besides being able to set the number of samples in the setup menu, there are a few fixes and improvements in the code, but possibly one of the more fundamental ones was changing the main loop from 10 loops per second down to 5. The reason is the slow interface to the LCD. We already knew it was slow in part 2, and so I designed the LCD panel module to keep a shadow display with the same content as the actual screen in local memory. If, for example, the run display uses 4 calls to write LCD to update the LCD screen, the function would first compare the text with the corresponding part of the shadow display. If they matched, as is the case here for the first, third and fourth example, white LCD would simply do nothing further, as the actual LCD screen already shows these values. For the second string, a difference would be detected, and so the white LCD would update the shadow display and send the whole update to the LCD. Well, this method works okay, but it's still wasteful to send the whole text string of 8 characters if only 1 or 2 characters are different. So the new software further reduces the amount of data sent to the LCD by only sending the actual changed characters. So in this particular case, same example, we would just send the character 5 at the corresponding position to get the display updated. At the same time, I went over the menus and removed almost all calls to clear LCD. It was kind of good practice that when a menu was finished, it would clear the screen so the next one had a free canvas to display whatever it implemented. It turned out that most menus are very similar in their text display, and almost all have the previous select, next and back text in the second row. So by not clearing the screen after each menu, the next one can fully benefit from the LCD write optimization. Sadly, while all this helps, it doesn't solve the fundamental issue that the speed of writing to the LCD tops at about 300 characters per second. If that sounds a lot, consider that writing a full screen of data that is 32 characters takes 106 milliseconds. With all the optimizations, most of the time the display update finishes much faster, but there are instances where this is not possible. For example, if lots of data in both rows changes very fast, or when leaving or entering the run menu. So there are occasions when the 100 millisecond loop time is exceeded a little. The program runs fine, of course, regardless, but I'd rather have a predictable fixed heartbeat, so I changed it to 200 milliseconds to give it reserves to cater for these fluctuations. This whole thing came to light when I recorded lots of data for the ADC investigations we discussed earlier, and that needed a steady time base. With a 200 millisecond loop time, the program runs fine, and if anything, it is more pleasantly to use with the noisy data, because at 5 Hz update rate, the display is much easier to read than with 10. For a change, I am using SSH to remotely access PowerMon via Wi-Fi, but a remote desktop using VNC would work just as well. So let's have a quick look at the data files, including the calibration data. The folder is INA and it contains a subfolder rec for recordings. Ignore the _py cache folder, which is created and managed by Python. Besides the .py source code, there are 3 text files: caldata.txt, limits.txt and setup.txt. No prizes for guessing what limits and setup files contain. If the program starts without finding a limits or setup file, it uses defaults. If you then change some setup data, it will create a new setup file. To create a new limits file, if none exists, press save in the limits menu. At the moment, there's only a very crude error handling on reading these files, and most importantly, this means if something in the format has changed with a new software version, you must manually delete the old setup text before starting the new software for the first time, or the program will most likely crash. In principle, the same procedure is true for the limits file, but that one has been stable for quite some time now, and I don't expect many changes that could affect the file format. Last not least, the caldata file. That one is different. The program will survive and use defaults if it isn't found, but it can't create it, and the display data would not be calibrated and could be very wrong. For example, if you're using a different shunt than the default of 0.1 ohm. This file is supposed to be created and edited by the user. Let's have a closer look at it. At first glance it may seem a little daunting, but it isn't as bad as it looks. Here's the structure of the cal data file. It consists of a pair of values for the bus voltage calibration, followed by one or more lines each defining a shunt resistor and its calibration in 4 ranges. Note that there is just one set for bus voltage calibration, as it's independent of the shunt resistor in use. For the shunt resistors you can have as many lines as you want. I'm showing 3 here, but you must have at least one. Each line is made of 3 parts. A friendly name that could be anything meaningful to help you identify and select that dataset, because that is the text shown in the setup menu. But it can't be longer than 8 characters. The next part is the nominal value of the shunt resistor in ohms. This is followed by 4 sets of 4 numbers each that make up the current calibration data for each of the shunt voltage ranges. I named them A to D because that's the range designation I use on the LCD display. The values shown here are needed even if you don't want to apply any real calibration. I think I mentioned that before. The choice of the word calibration by Texas Instruments is maybe a bit misleading. This is really mainly the configuration data, and it can be used for calibration as well. If you look at the formula that I selected for calibration, you realize that the default numbers of slope equal 1 and intercept equals 0 are such that the result x is always equal INA-x. In other words, no calibration. This is the reason why these values are set to 1 and 0. Before we get into this, where do you get these complicated looking default numbers for the current calibration, also known configuration data, from? I already explained that there's a rather convoluted 9-step procedure explained in the INA 219 datasheet for that. There's also a Windows program that you can download from the TI website for it, but that's not easy to use, and it's actually meant to be connected via USB to their evaluation board for the INA 219. While you can push it to work without a connection to calculate calibration data, it is not happy, and some of the data you entered resets suddenly without warning, presumably every time when the missing connection times out again. You can use a spreadsheet as I did originally, but in the end I decided to make a little Python program that does all the work for you. You find it in my GitHub page with the rest of the PowerMon code. You can run it on a PC or on a Raspberry Pi as long as you have Python 3 installed. The first thing it asks is the value of the shunt resistor in ohms. Let's use 0.1 ohm, which is the resistor that comes with the Adafruit INA 219 board. The program then calculates the minimum and maximum LSB for the first current range of plus minus 0.4 amps and asks you to choose a value within this range. The advice from Texas Instruments is to choose a convenient and round number close to the minimum LSB. Don't worry, the program won't let you enter values that are outside the allowed range. So if I type 0.01, which is clearly outside, it gives you an error message. I select 12.5 microamps. 1, 2, 5. Because I want a rather good resolution, and it works nicely. Next, the program asks the same question but for the 0.8 amp range. Here I select 25 microamps. which is close to the minimum and double the previous LSB, so that makes sense. For the 1.6 amp I picked 50 microamps. And for the last range of 3.2 amps I picked 100 microamps. The program then spits out the default calibration configuration data in a format you can directly use as a line in the cal data file. But how do you do actual calibration? The basic setup is relatively simple. We need to run a reference current through PowerMon and compare the INA 219 current reading with a trusted multimeter that has the same current flowing through it. A power supply that can be set to operate in constant current mode helps a lot, and it allows the trusted current meter to basically be a short circuit to ground, and the various test currents are set on the power supply. If you don't have a power supply that can handle this, you can use power resistors as loads to get the currents you want, but it becomes much more time consuming and the resistors may get very hot. In my case, the best multimeters for current that I have is the BM235, which has a 0.7% accuracy in the needed milliamps and amp range. My trusty old Solartron has a current range, but it's limited to 2 amps and a little out of calibration. For this reason I got this 10 milliohm shunt that has a 0.1 accuracy, and I use the highly accurate Solartron to measure voltage drop across it. This allows me to measure currents up to 10 amps with 0.1% accuracy, but I need to convert the display, which is in volts, to current. For a 10 milliohm resistor, this is straightforward. 1 amp flowing through a 0.01 ohms produces a drop of 10 millivolts. So I just need to read in millivolts and divide by 10 to get amps. One last remark on the setup: the BM235 has a milliamp range for up to 600 milliamps and a separate amp range for up to 10 amps. During these tests I'm running between 10 milliamps and 3.2 amps through the setup. It is very easy to keep looking at the INA 219 display and ramp up the current without looking at the BM235 and realizing that it's still set to milliamps. That is how I blew the fuse in the BM235, and let me tell you, these fuses are very difficult to get and outrageously expensive. If you don't want to end up buying a fake one from eBay, that is. In this test I'm testing range A as shown by the A in the upper left of the PowerMon LCD. I'm increasing the current from 20 milliamps to 400 milliamps in 20 milliamp steps. Continuing the test in range B from 400 milliamps to 800 milliamps in 20 milliamp increments. The BM235 is now in the amp setting. And continuing in range C from 800 milliamps to 1.6 amps, this time in 50 milliamp steps. The last range D from 1.6 amps to 3.2 amps in 100 milliamp steps. As designed, overflow is shown when exceeding 3.2 amps. Here are the results of the 4 runs in graphical format. The red line shows the difference between the reference instrument and the INA 219 reading on the left axis, and the yellow line is the error in percent on the right axis. The first observation is we actually don't need calibration. The error values are well within the 0.5% plus minus range. This is really good news, because it means even if you don't have a decent DMM to compare with, the INA 219 out of the box will get you very decent accuracy. The increase in error on the left side of the lowest range is actually an artifact of calculating the error. As you can see, the difference values are quite close to zero even at low currents, but the error increases exponentially because the lower the value, one LSB difference makes proportionally a huge error. I explained this issue already in the last video for a bus voltage. So practically minded people might as well leave calibration alone, but that's not what we're here for. If you look at the gray box, this is what the INA 219 datasheet recommends for calibration. Basically, you tweak the calreg value, which a chip needs to convert the shunt voltage into a current. You do that by picking a pair of reference and corresponding INA 219 readings to calculate a scale factor, which you then apply to the original calreg value to get the new calreg value. For example, if we apply 300 milliamps, but the INA 219 reads 303 milliamps, then you calculate the scale factor and end up with a new calreg of 32,444 instead of the original 32,768. Of course, you have to do this separately for each current range. Here's the spreadsheet that contains all the measured currents from the 4 test runs. You recognize the graphs, of course, but I want to show is the right side. I picked a row with fairly high currents in range A, and you see the calculation of the scale factor and the new calreg. I did the same for each of the other 3 ranges. And then applied the new calregs by editing the CalData text field. I repeated the same test runs as before, but using the modified CalData.txt. This sheet only contains the results for range A and D because I abandoned this approach halfway. The reason is easiest to see for range D. The yellow and red curves are the original data from the first run. The blue and green are the curves for the calibrated run. As you can see, this calibration method doesn't reduce the error at all. Instead, it merely shifts it vertically in the graph. Basically, the data point you picked when calculating the scale factor becomes the point at which has the least error, and the rest of the data is just moved upwards or downwards. A simple scale factor isn't going to correct this data, but if we use the same slope and intercept method I originally intended for just the bus voltage calibration, things improve drastically. Here you have the same data, but this time I picked 2 rows for each range to calculate the slope and intercept. As you can see here, for each of the 4 ranges. I then applied the correction formula to the original data, which you see in column E, calculated the new difference to the original data and the error in percent, and plotted the data together with the previous values. The difference compared to the calreg method is remarkable. This really corrects the error properly. Look just how close the blue and green lines are to 0 compared to the original values. Because it works so well, I changed the calibration data and method for currents to leave the calreg data alone and apply the slope and intercept method instead. This is the reason you see these additional fields for every current range in the CalData text file. For ease of comparing calibrated and uncalibrated current data, I actually created a second line for my built-in 0.1 ohm shunt and called it 0.1 cal-A. So all I need to do is to switch in setup to that shunt, and the unit will switch to use calibrated numbers I added into the slope and intercept fields. This calibration occurs, of course, in my software. From the chip's point of view, neither current or bus voltages are calibrated, which means its reported power values are also not calibrated. But in fact, I already decided in part 3 not to use the chip's power value and instead calculate my own power value. At that time, it was because the chip reports power as an unsigned value, when in fact it should have had the same sign as the current to reflect that power could be delivered or drawn. Here's a test run after I applied the slope and intercept method for current calibration. First I have to make sure that the right setup with the modified cal data is being used. For this run I increased the current in 50 mA steps from 50 mA onwards to 1 amp, and from then on in 100 mA steps all the way to 3.1 amps. The results in graphical format. With the calibration, the INA219 and the reference instrument track very closely, as you can see. The difference stays very close to zero over the whole 4 ranges. The error is under 0.1%, which is excellent. We already discussed the apparent rise on the left is a mathematical artifact of the way the error is calculated. Onwards to the bus voltage calibration. For that you need to be able to apply a constant voltage directly between the black and yellow terminals of the power mon. Make sure the unit is set to measure load voltage, and the bus voltage calibration line in the cal data file is reset to 1 and 0 in case you already did a bus voltage calibration before. Again, I'm using 2 meters to compare the INA219 with. Not essential for calibration, but more for convenience. Instead of writing down the readings on PowerMon, I use the manual recording method. To do that, use Setup to select Manual Recording option and then turn the recording on. Every time I press Select, the unit writes a snapshot of the data to the recording file. In the test run, I increased the voltage in steps of 0.5 volts from 1 volt to 20 volts and press Select to record the value. Using manual recording is an excellent time saver. Just remember to turn off recording at the end of the run to make the recording file accessible. The red line using the left y-axis shows the difference between the INA219 display and the reference, while the yellow line using the right axis showing the error in percent. As you can see, the differences all lie around a line, which means they will be easy to correct with calibration. To do just that, I picked 2 value pairs shown here in the data from the dataset to do the slope and intercept calculation. I then changed the bus voltage line in cal data.txt accordingly. I repeat the test run using the calibrated bus voltage setting. The voltage is increased in 1 volt increments from 1 volt to 20 volts. Just for good measures, let's test it against my reference standards. First against the 5 volt output of the DMM Check Plus. 5.00 volts as expected. And the 10 volt output of my AD588 reference standard shows us exactly 10.00 volts. As you can see, the bus voltage calibration worked and produced excellent results. Overall, I'm very happy how the calibration turned out, but it may be a bit manual for some and involves too many spreadsheets or calculator activities. Despair not, I put another method in as well. Well, you have to start with a cal data.txt file because there's no other way to come up with the cal rec and current LSB values, but as I showed already, there's a utility to help you doing that. So once you have that file, you can use a new calibration menu in PowerMon to calculate slope and intercept for you. Here's how it works. Once you enter the new calibration menu from the main menu, you can use Show to see 5 slope and intercept values, one set for bus volts with V in the left corner, and 4 for the current ranges A to D as determined by the current shunt value. You can select volt or each of the 4 current ranges. For example, I select volt. The program turns off any existing calibration temporarily and shows a target, here 1 volt on the left and the actual reading on the right. You need now to adjust the voltage of your power supply until your reference instrument shows the target voltage. It is important, don't look at the actual readout of the LCD, this is just for control. You need to look at your reference meter when adjusting the voltage. It's a bit awkward trying not to block the camera when I'm doing this. Once you have it, press Cell and the program prompts you for the second target. I'm using 5% and 95% of the range as targets. Repeat the process in adjusting the voltage until your reference meter shows the target value. Press Cell again and the program calculates the calibration data, applies it and updates caldata.txt at the same time. The process works the same way for current ranges, except that you need, of course, to match the displayed current targets. And that's it for this part. The PowerMon is now fully functional and calibrated and ready for action. As always, the source code and schematics are available on the GitHub page. Thanks for watching.